Yo, we back with another video, y'all. Welcome back, man. You can see my beard still trying to come through, but that's not the point, y'all. We here to learn some coding. I got about 30 minutes. Yeah, I enrolled into EDX, y'all. I'm gonna show y'all what that is in a second. EDX, y'all. I'm gonna show y'all what that is in a. All right, just wanted to make sure that my audio's coming through clean and crispy. You heard? So yeah, we got the crispy clean audio coming through. There we go. Okay, so let's see. So right here, y'all, this is Harvard CS50. Now, if y'all know about coding, y'all probably heard about this. I've been seeing a lot of reviews about whether to not or not to do this or not. But hey, man, I like to know stuff. I like to understand what I'm doing. I'm not even sharing my screen with y'all, and I'm trying to act like I am. Let me get that right. All right, here we go. Share. Boom. So right here it is, y'all. This is free on YouTube also, so you guys can type in CS50 and you can watch these same curriculum that I'm about to get into. But I'm gonna do it on here so I can kind of hold myself accountable and track my progress. So let's get into it, y'all. We're gonna be watching this. We're gonna be so all this. That thing loud. I don't know if y'all hearing that through my computer or through the mic, but either way, here we go. Walking 2 times the speed? No, I ain't gonna. I might. The illustrious, eloquent, prestigious Harvard University. No idea where this is at. Somewhere on the East Coast. The Ivy League school, y'all. Oh, it's the Ivy League introduction for sure. David J. Malin, he's supposed to be the guy over there. CA50. Man, don't let me get into Harvard. I'll be like Redman and Method Man in that thing. Should I pull up I should pull up cursor, huh? Probably. Wow. This is CS50. Let's get to it. David J. Malin. This became a big deal over the internet, y'all. So I'm glad this is free stuff at Harvard.
All right. This is CS50, Harvard University's Introduction to the Intellect.
Hey, YouTube, don't flag me for watching this video, y'all. This ain't even on y'all platform, so technically this is free already. So I hope y'all ain't got no copyright infringement. Disclaimer: I do not own the rights to any of this shit. Maybe I should put that in the description so these suckers know that I ain't trying to steal their stuff. Can I do that while I'm live? I might do that while I'm live so I can make sure that I don't get flagged.
Actual enterprises of computer science and the art of programming. My name is David Malin, and I actually took this class myself some years ago, but I almost didn't. It was my first year in college, and my roommates and I were living in Matthews Hall, for those familiar. Nice, Matthews.
Never heard of it.
Our claim to fame, actually, at the time, was that our room was literally Matt Damon's just 3 years prior. So onward from
I didn't know Matt Damon went to Harvard.
that. But my first year, I didn't really have the nerves to like set foot in this classroom, let alone computer science. In fact, for me, computer science and CS50 in particular was very much this class to beware. Like I was kind of comfortable with computers, but I certainly wasn't among those more comfortable with computers. And so I shied away my first year. Instead, I actually took a whole lot of classes in government. In fact, in high school, I was really enjoying history. I loved this constitutional law class that I took my senior year of high school. And so I figured, okay, if that's what I liked in high school, and if that's where my comfort zone was, that's probably what I should be doing in college. And so I essentially declared as my concentration or major government for the first year and a half of school. But my sophomore year, when I was living actually in Mather House instead, okay, no one from Mather. In Mather House instead, it was.
Time out. Let me put this disclaimer up there, y'all, so y'all know that your boy does not own the rights. I'm learning the code following the Harvard CS50 curriculum as a complete inventor. I have zero coding experience. This series documents my real unfiltered journey from absolute beginner to hopefully creating an AI trading bot. Disclaimer: following Harvard CS50 to learn coding from absolute zero, not a tutorial, financial advice, or expert guidance. Just documenting my guidance learning journey from complete beginner onwards. Yeah. So, well, that's not even what I wanted to say. I don't own the rights to this. That's what I wanted to say. Moving forward.
I sort of followed some friends, I think the first week of class in September of that year, to a class called CS50. And honestly, like once I stepped foot in that classroom, the professor at the time was a famous computer scientist by the name of Brian Kernighan, now at Princeton. Like I was hooked, and literally would I go back thereafter on Friday evenings when at the time problem sets were released and like sit down at like 7, 8 p.m. on Friday.
There's something about this rubber duck too. I guess you can ask the rubber duck questions if you actually go to the class. They coded a robot, rubber duck or something. I don't know.
Friday nights and like dive into homework, which isn't necessarily something we recommend per se, but for me, it was like this sign that like, wow, I've sort of found my calling. I found my classmates here on campus. And that's not going to be the case for everyone. Certainly, we have no expectations that after taking one computer science class that you will or might want to take others. But what's so empowering about computer science and CS50 in particular is it's so applicable to the broader world, whether you're in the arts, humanities, social sciences, natural sciences, or beyond. It's just so applicable, the concepts and the practical programming skills with which you will exit a class like this. Now, it's going to be challenging along the way. And indeed, I put in my time back in the day, and even I did find it challenging. And here, for instance, is a photograph of a very famous MIT hack, so to speak, from down the road, whereby it communicates that getting an education from MIT is like trying to drink from a fire hose, which is to say there's going to be so much information, like so much new stuff, that certainly on any given day of the week, you're not going to be able to absorb all of it that first time around. But at the end of the day, it's through that challenge, putting the time in, that the returns are therefore just so much higher at the end of the course. And indeed, will you walk out of the course with a much better understanding, not only of computer science and programming, but ultimately how to teach yourself new technologies and beyond. For the next 3+ months, well, we have teaching fellows, teaching assistants, course assistants, and myself by your side, sort of guiding you through the course's material. But the goal by term's end is to take those and leave those training wheels off so that you're well equipped to sort of go teach yourself new ideas beyond the class itself. Take comfort, though, in knowing that most CS50 students have never taken a CS course before. And indeed, as per the syllabus, what ultimately matters in this course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. And
I like that. I like that. It's not you versus anybody else. It's you versus you. It's not you versus the progress of your classmate. It's you versus where you started from. I like that. All right, David Malin.
When you began is thus today. And so consider just how comfortable or uncomfortable you are with computing, let alone computer science and programming, particularly if you've never explored either in a classroom before. And consider the delta just a few months from now that will really describe how far you have come. And that is all that matters, not how much the student to the left, to the right, in front, or behind you right now knows. With that said, let me add some additional inspiration, if I may. Here's a photograph of my own very first homework assignment in CS50 from.
Let me read this. Hello, C assignment, name, David Malin, a program to print hello. Hello, CS50 on the screen. Include, did he type this up? -2 for hello. .out, we worked output of hello, not of make.
From 1996. And I will draw your attention to the fact that even though this is a so-called Hello World program that we'll play with ourselves next week, it is pretty much literally the shortest, easiest program you can write in a programming language called C. I still somehow got -2 on my very first homework assignment, which is to say, like, we're all going to make mistakes along the way, but the goal will be to learn and enjoy that process here on out. The end of the day, too, like me, you'll exit with your own proudly held I took CS50 t-shirt, as is our tradition too. With that said, there's so many other traditions within CS50, both on campus and off. And in particular, do we try in CS50 to provide not only the academic support structure that you might want going through the class, but also a collective shared community experience, which is to say in just a few days, we'll start off the term formally with CS50 Puzzle Day, which is not only an opportunity to get together with friends, with pizza and prizes and also logic puzzles of sorts, but really to send the message that computer science itself is not about programming, it's not about C, it's not about Python, it's not about programming languages per se, but about problem solving.
It's about all that.
More so collaboratively with other smart people by your side in this class or beyond. And indeed, are there toward the end of the semester reinforcements of the same by way of a little something that we call the CS50 Hackathon, which will be an opportunity overnight to dive into your own final projects, the capstone of this course, thereafter followed by the CS50 Fair, which will be a campus-wide exhibition for students, faculty, and staff across campus of your very own final projects, be it your very own web app or mobile app or anything else you decide to create by term's end. And indeed, the sort of
Gotta speed it up, my boy.
objective at the end of the day, truly, with that final project in particular, is going to be to create for yourselves, for your classmates, for attendees, something that we didn't even teach you how to do. And indeed, that will signal ultimately that you're indeed on your way and ready. Toward that end, thought we would give you a sense of CS50's past by way of the short video, if we could dim the lights, that paints a picture of all that awaits here and beyond. Becomes chasing.
Oh, snap.
Decide to create unary or people figuring out 30. All right, come, and that is all that teach yourself. It's like trying to drifty from 1996. It's not about C, it's not about Python. It's
Not gonna lie, it'd be pretty dope to be up in there, y'all. To be at a Harvard school. Oh, shout out to the Queen who was just on there. I ain't go to college, all right? I ain't go to college, y'all. But it's all good. Because of the internet, you don't have to shout to the Queen right there also. Um I'm going to Harvard for free online right now.
science itself. So what is computer science? Well, put simply, it's the study of information. Like, how do you represent it and how do you process it? But more fundamentally, what we'll teach in this class is computational thinking. That is to say, the application of ideas from computer science to problems of interest to us within the class and problems of interest to you after the class. And so at the end of the day, what computer science really is about problem solving, ergo that sort of global applicability. And by problem solving, we mean something quite simple. In fact, we can distill it as follows with this mental image. Problem solving is to actually produce a solution. So the output in this model would be the solution. The interesting part ultimately is going to be in how you process that input and turn it into that output, ergo solving problems. But before we can do that, we all kind of have to agree how to represent these inputs and outputs, especially if we want
Okay, I like how you broke that down. Simply input and
to
output.
do it in a standardized global way using literally computers, be them laptops, desktops, phones, or most any other kind of electronic device nowadays. So how can we do that? Well, there's different ways to represent information in the world. For instance, if I were to take attendance old school style, maybe in a smaller room, I might do 1, 2, 3, 4, 5, 6, 7, and so forth, and just count people on my human hands. That's actually known as unary notation, otherwise mathematically known as base 1, because you're using your fingers literally in this model as digits.
Hold on, let me get the notes out now. Let me get my notepad out now. I forgot I'm gonna have to do that. Let me pull up my Google Docs. You know what I'm saying? Let's write this down. Google Docs. Actually, let me switch my account so I'm got the relevant account popping. You know what I'm saying? I'm about to get this. I'm about to get straight A's. Yo, I'm a straight A Harvard student. You heard? My boy David Malin. Run up on the boy. What is it? Docs? Where my Google Docs at? Oh, here we go. CS50 day 0 scratch. Let's get these notes popping. CS50 day 0 scratch. Damn, why that shit so small? Can't even see that. What percent is it at? There we go. What was that? 80, 70%? Make that the title. See, and now we got ChatGPT, so I can cheat on my homework. I'm just playing, y'all. I'm not going to cheat on my homework. Let's center that. Okay. My boy said unary, and that's base 1. Oh, I seen a video about this with what's his name? My boy. What's his name? Can't get off me. That's Can I switch this to something else? Okay, whatever. I don't know why it's doing me like that. Unary equals base dash 1. My boy Neil deGrasse Tyson. I seen a video with Neil deGrasse Tyson talking about this. Let's continue.
But little quick question, how high can you count with one human hand?
You can go to 5.
5 is incorrect if
4, because you start with 0.
you use a different base system than 1. So it's obviously correct if you're just using unary and just counting 1, 2, 3, 4, 5. But I dare say I can come up with more patterns in my human hand alone that would enable me, without a second hand or a couple of feet, to count higher than 5.
Oh, he got me.
In fact, maybe for those more comfortable, how high could you actually count on a single human hand, perhaps? So 31, believe it or not, is in fact the correct answer. But why? Well, here I initially started pretty naively.
Time out. Okay. Base 1. On your hand, you can count to 31. I don't know why.
1, 2, 3, 4, 5. And I just kind of combined all of my fingers and counted the collective total. But what if I'm a little more clever and take into account the pattern of fingers that go up? So maybe this is still 0. This is 1. But now maybe we just agree universally that this is 2, even though it's just my single pointer finger. Maybe we all just agree that this is 3 with 2 fingers up. Maybe we agree that this is often offensive with just 1 middle finger up, but this would then be 4.
I'm counting to 4.
This could then be 5. This could then be 6. This could be 7. And if I keep permuting my fingers in this way, allow me to spoil it, this would be, in fact, 31. But
okay. So how would I write that? That's like saying the pattern of putting up a finger can represent a number, and the combination of those can represent a new number, essentially. Okay, let's continue.
But again, why? But the difference here is that we're no longer using unary, or base 1, as a mathematician would say, but rather base 2. Because if we take into account not just the total number of fingers that I'm using, but whether each finger is down or up, being therefore in 2 potential states, down, up.
Base 2. 2 potential states. Okay.
Up, A, B, black, white, however you want to distinguish those 2 states of the world, you're now operating what's called base 2. And perhaps more familiarly, even if you're not a computer person per se, this is the so-called binary system. And odds are, even if you're not a computer science person at all, you probably generally know the computers only understand or speak what alphabet, so to speak. So ones and zeros and ones, otherwise known as the binary system. And in fact, there's a term of art here that's worth noting. When you're using zeros and ones, which
my boy's sweating. He teaching for y'all. Y'all better pick it up, you Harvard students.
Of course, are a total of 2 digits. You have binary digits, so to speak, bi implying 2, which means there's
binary digits. Okay, dang that. Okay, he coming with that fire. He cooking. Binary digits. I'm gonna have to go ahead and review my notes already. I only got 12 minutes of information. I'm like, hold on, my boy. Binary digits. Okay. I like it.
2 possibilities, 0 or 1. If we actually get rid of some of these letters and then join these 2 phrases, here you have a technical term that is a bit. A bit is just a binary digit, which is to say it's a 0.
Okay. A bit is just a binary digit. Bit is just a binary digit. Okay.
0 or 1.
Which is a 0 or 1. Which is a 0 or 1. Okay, cool.
And this is in contrast, of course, with the system you and I know as the decimal system.
In contrast to the decimal system. Okay.
Dec implying 10, because in the real world, you and I daily use 0 through 9, which is 10 possibilities. Computers only use 0 and 1. that is to say 2 bits, to represent information instead. So how do we represent this information, especially when at the end of the day, what we're using are indeed computers and electronic devices? Well, if I want to represent 0, I can actually think of this as kind of analogous to the physical world. Maybe I have a light bulb that's off or on, controlled by a switch that turns it off or on. So you can think of a binary digit that is a 0 as really just being a light bulb that is off. By contrast,
Binary digit is 0, or a light switch that is off or on, for example. I like that example.
if you think of a 1 in the digital world as, of course, being the second of 2 possibilities, you can think of that in the human or analog world, the physical world, as being a light bulb that is on. And in fact, what's inside of your Mac, your PC, your Android phone, your iPhone are millions of tiny little light switches known as transistors that just can be turned on or off.
Transistors. Okay. You said they're what? Oh, I'm gonna go back a little bit. 13. See, this is gonna be the scrubbing system. Better be okay. Not
And
bad.
in fact, what's inside of your Mac, your PC, your Android phone, your iPhone are millions of tiny little light switches known as transistors.
Okay, boom.
That just can be turned
See.
on or off. And essentially, you can use those transistors to store information, because if you want to store a 0, you turn one of those switches off. If you want to store a 1, you turn one of those switches on. Of course, that sort of invites the question, well, how do we count higher than 0 or 1? Well, we would seem to need to use more than just maybe a single bit, a single light bulb. So if we wanted to count higher than, for instance, 0 or 1, why don't we go ahead and maybe do this? So just so I have some place to put these, let me borrow some of our actual physical light bulbs here from the stage. And let me propose that now, with 3 bits on the stage, 3 light switches, 3 transistors, whatever metaphor you're most comfortable with, this is how a computer would represent.
Bits, light bulb, transistors. Bits, light bulbs, transistors. Just so I can keep it in mind.
Present a 0 because all of them are off. So it's off, off, off. But if a computer wanted to count to 1, we could do naively this. We could turn this on. And if a computer wanted to represent 2, we could do this. And if a computer wanted to represent 3, we could do this. But I'm kind of painting myself in.
He said 31 was base 1 with 2, or well, 5. So I'm guessing like what, like, I don't know, 15? 7. So it's a combination, all right? So 1 on, and then these 2 off is 1. This one on, and these 2 off is 1. This one on, these 2 off is another number. But then these 2 on would mean this is a number. These 2 on would be a number. So okay, I can see it. 1. Mm, okay. Oh, time out. What happened? I'm not sharing my screen. Am I sharing my screen with y'all? Can y'all see this? Hold on. I don't think. What happened? Want y'all to pick up on this game. He dropping some sauce right now, y'all. We in C50. We in Harvard, y'all. Let's get it.
My finger, I did this with 2 fingers. Well, I'm going to turn this one on. This is 3. Now, this will, for those less comfortable, be non-obvious. This now is how I would represent the number 4. This is how I would represent 5. This is how I would represent 6. And this, as per the spoiler, is how I would represent 7. So perhaps very non-obvious what it was I just did or why I chose those patterns. But I dare say if you sort of rewind in your mind's eye or literally later on video, you'll find that I actually did show you 8 distinct patterns of light bulbs. The first one was off, off, off. The last one was on, on, on. And there were another 6 total in between then. Well, wait, why 7? Well, if you start counting at 0, and I claim there's 8 possibilities, you can only count from 0 to 7, as we will soon see. So how are these patterns coming about, and what is it that our computers are actually doing? Well, it's actually doing something a little like this, quite like in decimal. So in the human world, you and I are very much in the habit of using base 10, 0 through 9, aka decimal. Well, how do we use it instinctively as humans? Well, what's this number obviously on the screen?
Dang. Time out. It keeps closing my it keeps closing my video share. I don't know why. I wonder if it's because it's flagging me, telling me, hell no, you can't be watching Harvard. But it's on YouTube for free, so I'm just reacting to this. I don't know. Let's see, because I'm watching myself on another phone on my phone to see what it's looking like. So I'm gonna stop sharing and I'm gonna go back. I'm gonna share it again. Let me see.
Is in the tens column. This digit is in the hundreds column.
I think I might have to stop like every few seconds to do commentary so I can use that free copyright shit. The free like fair use.
And so forth. So even though none of us have to do this math explicitly, what you're instantly doing is 100 times 1 plus 10 times 2 plus 1 times 3, which gives you 100 plus 20 plus 3. Oh, that's why it is 123, because these digits in this order have that significance.
True. Okay, I see. He said that's base 10. Base 10 is 1 through 9. What we use on a daily basis. Cool.
Digits to the left have more weight, so to speak, than the digits to the right. So what can we take away from this? Well, let's generalize it first. It's just any 3-digit number. So number, the ones column, the tens column, the hundreds column. But there's some math going on there, and it's not particularly sophisticated. Those are actually powers of 10. So 10 to the 0, 10 to the 1, 10 to the 2. And there's your decimal system. Because the base in this value is a 10, that's
ones place, the tens place, the hundreds place.
Because there's 10 possibilities for each of those placeholders, 0 through 9. But in the binary world, in the world of computers, where all they have are zeros and ones, why? Because all they have physically is transistors, tiny, tiny, tiny light bulbs that can be off or on. If you only have have 2 digits to play with, the 10 base should, of course, become a 2 base. And now if we do some math here, 2 to the 0, 2 to the 1, and 2 to the 2, you get the ones column, the twos column, the fours column. And if we keep going, 8, 16, 32, 64, 128, and so forth, it's powers of 2 instead of powers of 10. But this is to say computers represent information in exactly the same way you and I have since childhood, but they have fewer digits at their disposal. So these columns need to be weighted differently. So
okay, let me marinate on that real quick. 10, because 10 to the first power is 10, 10 to the second power is 100.
we can still count from 0 all the way up toward infinity. So what does this mean? Well, here we have 3 bits on the screen, 0, 0, 0. If we were to convert this now mentally or on paper pencil to decimal, how do we do it? Well,
good question.
4 times 0 plus 2 times 0 plus 1 times 0, that gives us the mathematical number you and I know as 0. That was 3 light bulbs, off, off, off. Well, what if we turn on 1 light bulb all the way on the right? What decimal number does this binary number, 001, represent?
What decimal number? It's either 1 or 0.1.
Just 1, because it's 4
Okay.
times 0, 2 times 0, 1 times 1. Here's where things got more interesting, even if non-obvious in light bulb form or even physical hand form. 0, 1, 0 in binary is what in decimal?
2.
2, because it's 2 times 1, and that's it. 0, 1, 1 in binary is, of course, now
11.
3.
Oh, what? Oh, and binary. Okay. 2 times 1 is 2. 1 times 1 is 1. Add them together is 3.
This is now
400. 4 times 1.
4.
Oh, no. Okay, I see. 4. Because he's
This is now 5.
5. 4 and 1 is 5.
This is now 6.
6. 4 times 1. 2 times 1. Okay.
And 7 on, or 1, 1, 1
4 plus 2 plus 1 equals 7.
is the highest we can count with these 3 bits. All right, so how might a computer intuitively count as high as 8?
You're going to have to add another. You have to add another number.
What do you need to do, presumably?
Add another number.
You're going to need to add a bit. So you need another
bit.
light bulb, another switch. You need more memory, so to speak, to use nomenclature with which you're probably familiar. So in fact, if we change all of those to 0, but we give ourselves 1 more bit for a total of 4, that's got to be the 8th place, because it's just another power of 2. So 1000 is the decimal.
Time out. I didn't know there was this much math in computer science, but I can dig with it. I can dig it, y'all. I'm out here learning, y'all.
Number 8. You don't say 1000 in binary. You literally say 1000, but that is the number you and I know as 8. And you can keep going up and up and up.
I'm about to start. Yeah. Okay. So next one will be 16. So could I get my age from that? So I'll be 16 plus 8 is 24 plus 4 is 28. So no, see, I would need 32. I would need a 32-bit. So I would be, my age in binary is 100000. Damn, I'm old.
And how then computers with Excel or any kind of number crunching software count really high and keep track of really big numbers? The computer just throws more and more transistors at it, more and more bits to count higher and higher and higher than this. Turns out though, 1 bit, 3 bits, even 4 bits aren't that useful in practice, because like literally you can count as high as 7 or maybe 15 or 31. So more commonly, as is commonly known, is to use a byte.
A byte. Okay, well, let's get it. So a binary uses 1 and 0s, and then the transistors are powers of 2s. Binary uses 1s and 0s, and the transistors. I mean, I know there's a better word for this. I'm gonna throw my notes in the chat GPT to be like, hey, can you make sense of my notes? So now let's get into byte.
Of bits instead. How many bits is in a byte, for those familiar?
How many bits in a byte? 10?
So it's just 8. Why 8?
8? Okay, I was wrong.
It's just more useful than 1 or 2 or 3.
All right, y'all. That's all I got time for right now, man. I gotta go to this appointment. I'm 21 minutes in. I got some notes here. I appreciate y'all. This is day 5. Maybe I'll be back today to continue day 5, part 2. I'm unsure, but right now, that's all I have time for. I'm gonna keep coming back, and I'm gonna keep learning. I'm gonna keep doing this CS, and I'm gonna get this dang trading bot up and online. But my main goal is to learn Python. I have another course that I believe I'm gonna start taking here soon. Is actually focused on building an algo bot, but I need to understand the back end and the actual how to build this. You know, he's kind of just walking us through how to build it, but I need to understand the science behind it, the computer science behind it. So appreciate all y'all. Peace to all the rebels. I'll be back.